All right, so we're going to take a break from loops for a little bit before we get back to and talk about renormalization. And I want to talk a little bit about symmetries. Close the stupid thing. All right. So we've talked about symmetries a little bit, I think, when we were talking about classical field theory. Okay, and I mentioned the importance of symmetries in quantum field theory, symmetries in nature in quantum field theory, because it's basically what the tool that we use, or the piece of information that we use to guide us in how we construct our quantum field theories. Okay, so because how do I want to say it? Well, we basically use Nether's theorem, okay, because we notice. So the way it typically works is, so take the electromagnetic interaction as an example, right? We notice that in these interactions we always conserve charge, right? So there's some conserved charge or some conserved current, right? And we could use so Nether's theorem is telling us that because we have a conserved charge, there must be some symmetry, right? Some symmetry in nature that gives us that. And so what in that symmetry, we can formulate it as just a normal U1 type of symmetry, right? And then we can use that to tell us what terms to write down in the Lagrangian. Okay, so we use symmetries to tell us, to basically, tell us what terms we can write down in the Lagrangian, which terms are not, don't follow that symmetry, and if they don't follow that symmetry, then we just drop them. Okay, and that's what's used, to construct theories beyond the standard model, right? So you hear things about supersymmetry, right? So that's based on some symmetry in nature, and there are terms that you can write down in the Lagrangian that obey that symmetry, and then there are terms that don't. Right? So you drop those terms when you write down the Lagrangian. Okay. Anyway, so we'll see, as we go along, the importance of symmetries in quantum field theory. But it's basically the foundation on what quantum field theory is built on, and it's the achievements that it's made have been based on symmetry.
What's the story behind the first image?
Oh, I don't know. There's something creepy. I just searched for symmetries. It says Dr. Perky's symmetrical circus. Yeah, I don't know. When I was writing these slides, I was just in a weird time in my life. No, I'm just kidding. I don't know. You'll see there's other slides or other talks that start off with weird slides too. Okay. All right, so we're going to talk about symmetries. Let's first talk about continuous symmetries. Okay, so and as an example, I want to consider a theory where I have A scalar fields. Okay, so or let's say N scalar fields, and I denote those different scalar fields by some subscript A. Okay, and so I want to write down the Lagrangian for this guy, and it's just going to be a function of the fields and their four derivatives. Okay, and we talked a little bit when we were talking about classical field theory that this type of Lagrangian is invariant under these types of transformations, right? It's just like a linear type of transformation, because what you find is that the Lagrangian transforms in the same way, and these terms don't contribute to anything that any observables. Okay, but let's compute that shift explicitly for this field, or for this theory where we have n fields. Okay, just using the chain rule, right? So L is a function of the field and its four derivative, right? So I have the first term, which is the derivative with respect to the field, the second term, which is the derivative with respect to the four derivative of the field. Okay, and if we use the principle of least action, we know that the variation of S with respect to the field is zero. That's the definition of the principle of least action. Okay, and so I can use that up there along with this definition. Okay, so I know that this thing is this, right? And this, I can use the chain rule again, so this is just restating that up there, all right? And then what do? I'm taking, how do I get this delta function? Oh, because I'm taking the basically the derivative of phi b with respect to phi a, and that's just a Kronecker delta function. And the arguments give you this four-dimensional delta function. Okay. So you see, I wrote down my Lagrangian in terms of phi b, just to denote, just to be general. Okay. All right. So what does that get us? So we can do, like we always do in these things, we can do an integration by parts, right? And I can drop the surface term because I know that that's going to give me, it's not going to give any contribution, right? And then using the delta function, I can get down to something that looks like this for the, basically the variance of the action, okay? Now what do I want to do? I want to take, so I'm going to use this equation in what we wrote down before, the variation of the Lagrangian. Okay, so I'm going to use that to replace one of the terms that I have up there. Which one is it? It looks like it's the first term. So the term that looks like dl d phi, I'm replacing it with this guy. So I'm taking dl d phi here, I'm replacing it with this stuff. Okay, and I get something that looks like this. Okay. But this guy, you notice that the first and the third terms, so this is the derivative of this junk times that junk and the derivative of that, right? And that's just the chain rule. So it looks like a total derivative of some term, okay? So you whittled the variance of the Lagrangian down to a total derivative plus this stuff, right? And this stuff, we know from the principle of least action, is 0, okay? So I've just done some algebraic tricks to basically get down to the point where I can say, okay, I see that this is 0, and I know that this is 0, right? We said that in the beginning, right? So it's telling me that the four divergence of whatever this stuff is in the brackets is conserved. Well, it's 0, so it means that the stuff in this bracket is conserved, okay? And that stuff we give a special name. We call it the current, the forecurrent. Okay, we saw a little bit of this before. So in general, we could write down an equation that looks like this. Second term will vanish. Yeah, we know that. What we've seen before. Okay. All right. So what we've got in this black box is basically another's theorem, right? That tells us that for every continuous symmetry that leaves the Lagrangian invariant, in other words, delta L is equal to 0, there's a conserved current, right? So we know that this term goes to 0 as long as there's some symmetry, as long as the symmetry or the Lagrangian obeys the symmetry, this term will be 0, which will tell us that there's a conserved current. Right? Right? Everybody agree? Okay. So this equation 11 is just a formulation of Nether's theorem in field theory. All right? So as long as the Lagrangian is invariant under some symmetry, there's a conserved current. Right? Everybody cool with that? Okay. All right. We can sometimes you expand it out. So just expanding out the mu's there, and you can write down something called a charge density and a current density. Okay, the 3 current density, and typically we won't work that much with those things, but you'll see it in the literature sometimes. Okay. All right, so that was for a case where we had, in identical fields, basically phi A, phi 1, phi 2, phi 3. Let's look at a case that's of interest because, well, it's important because it's what the Higgs theory is based on. But is a theory of complex scalar fields. Okay, and meaning that the field is not real anymore. Right? So phi and phi dagger are different. In general, they're different. Okay, and so the Lagrangian for that is this. Right? So this is the the normal kinetic term, the mass term, and there's an interaction term. So this is like lambda phi to the fourth theory. Okay. And so when you work with this theory, you basically have two choices. You can work with phi and phi dagger and treat those as separate fields, right? So when you go and compute, say, the Euler-Lagrange equations of motion, you're going to have two equations, right? One for phi and one for phi dagger. Right? Or you can put it in a more familiar form by writing phi and phi dagger in terms of their real and imaginary parts. Right? So I can write phi in terms of its real and imaginary part, and then phi dagger is just the same, but the minus sign here from taking the Hermitian conjugate. Okay? And what that buys you is you get away from this mixed term right here. So this thing will cause you some headaches, right? But if you use this formulation, you get down to something that looks like just a combination of two Klein-Gordon equations, basically, or two Klein-Gordon fields. Okay? And so you get some terms. So you get the normal derivative and mass terms, and then your phi to the fourth term looks like that. Okay? So that's the typical approach when you want to work with a complex field, is to do away with phi and phi dagger and work with the real and imaginary components. Okay? But what about symmetries? Well, we can look at this guy and we can say, well, yeah, I can multiply this guy by some e to the I something, right? The phi field, right? And when I take phi dagger, I should get a symmetry. In other words, because these terms, because phi and phi dagger always appear together, right? So if I multiply phi, I have it on the next slide. If I multiply phi by some e to the minus I alpha, where alpha is some real constant, then I take phi dagger, it's going to give me e to the plus I alpha phi dagger. Those exponents are going to cancel out. I'm going to end up with the same thing I had before. Okay? So this is an example of a symmetry, right? So I can do some transformation on the field, even though it's just multiplying it by some constant, right? But it's a transformation, right? And the Lagrangian's invariant under it, so it's a symmetry. It's a symmetry of the Lagrangian, right? And it turns out that it's a U1 transformation. So it's a transformation by one unit. So 1 by 1. This is the number, unitary matrix. Okay, that's why I put matrix in quotation marks. Okay, so it's just a U1 transformation. All right. But what about, so that's in terms of phi and phi dagger, right? That doesn't really work with our other form of the Lagrangian, right? Because here we've got phi 1s and we've got phi 2s, right? So it's not going to be it's not going to be like an e to the I alpha type of transformation. It's going to be more what we would call a rotation, right? It's going to rotate phi 1 and phi 2 into each other. All right? There's going to be some admixtures now, okay? And so the way we usually do this is to write it in terms of a doublet, which is basically just a two-column, what's the same, vector, right? And we parameterize that rotation by just a normal, like a two-dimensional rotation that you're used to from grade school, right? Right? And alpha, again, is our real parameter, okay? And you find that if I take this guy and I replace it with this stuff, after I multiply all this stuff out, right, and put it back into this Lagrangian, that all those sines and cosines are going to get combined, and I'm going to end up with the same thing that I had before, okay? Which is a good thing, because we already saw in when we looked at the theory in terms of phi and phi dagger that it had some symmetry, right? But now we see that for phi 1 and phi 2, it also has a symmetry, which is basically just a rotation, right? It's a rotation matrix. Or if you want to be fancy schmancy, you can call it SO2 transformation, okay? It's just a rotation, right? Or rotating the fields. Okay. Yeah. So, like I said, if you know, mathematicians, you know how they are. They always like to throw out fancy words, right? So in group theory, you would say, oh, you know, the U1 transformation maps into an SO2 transformation, obviously. All right. So we've seen that one theory can be written in two different ways. The symmetries have, or, you know, the transformations have different forms, but they mean the same thing. Okay. And oh yeah, man, I used to be a lot tougher. I assigned this for a homework problem, but you can compute the currents for this theory, right? And they look something like that. Remember, the double arrow means that you're acting on, you know, there's one term where you're acting to the right, and one term where you're acting to the left. Okay. All right. So that's an example of a continuous symmetry for a real world type of theory. All right, so what I want to do now is try to understand, you know, Nether's theorem, or the implications of what we would call Nether current and quantum field theory using our path interval formalism. All right, so to see, you know, what it means for our path interval formalism. Okay, so I'm going to start with our friend. So we're going back to this theory where we have n fields. Okay, and I'll label them as phi a. All right. So we're going to write down our old friend, the generating functional, right? So we have our action, and then we have our source terms, okay? And we hope, we know, or we think, one of the three, that under an infinitesimal shift like this, that the generating functional better be invariant, okay? All right, and in fact, if we assume that it's invariant, and we carry out the like we do a variation of both sides, when we hit this guy, the exponent is going to bring down this factor right here, right? And so we get something that looks like this, right? But we've seen that we can always equate these types of integrals with time-ordered products of operators. Remember, that's how we go back and forth between the two, all right? And you know, and the way we get those are basically taking functional derivatives of our generating functional. Right? So let's take n functional derivatives with respect to j and some subscript aj that's different from a, and some argument xj, and then we'll set it equal to 0. All right. All right. So it's going to be messy, right? And so we're taking n functional derivatives of this thing, and what we get are basically two terms, right? Because what? So when I take a functional derivative of the first term, I'm going to get the normal stuff that we're used to getting, right? But then I'm going to have terms where I'm taking functional derivatives of this, and it's going to pick out this term, right? So my functional derivatives are going to basically have are going to give me two terms, two forms. One is this guy, right? And the other comes from this term, the JA term, because remember, this has argument x, and I'm taking functional derivatives with respect to some other x and some other a. So it's going to give me delta functions, right? And so that's what this is. Okay, but there's n, we're taking n functional derivatives, all right? So there's going to be n of these terms that look like this, okay? Okay. All right.
This d phi in the beginning is multiplication of each phi.
Where? Oh, the d phi? That's the path interval.
It's multiplication of.
Oh, yeah. You have integrations over each field. Is that what you mean? Yeah.
It's equal to d phi a1, d phi a2.
Yeah.
And so on.
Yeah. It works exactly the same way. You can lump them all together in that thing, and as we've seen, you know, from our Klein-Gordon theory, you know, whatever that thing is, it doesn't matter at the end of the day.
Before we just had one field?
Yeah, but you have to integrate over each field. Yeah, good point. Okay. So what do we want to do? So we want to, we know that, okay, so now we're using the fact that we know that this thing has to be arbitrary, right, except at the endpoints. Okay. So we can drop it and basically work with the stuff in the square brackets, all right? So it's telling us that the stuff in the square brackets has to be 0, right, because the left-hand side is 0, okay? So what do? Well, we can first go from this path integral formalism to our time-ordered products of operators, right? So we've taken our n functional derivatives, so I can replace, or I can make the, the connection between this term and this guy, right? This is what we did before when we went back and forth between the path integral and the time-ordered products of operators, right? So taking n functional derivatives is giving me these time-ordered products of operators. Okay? So the top term in 22 corresponds to the top term in 23, and the bottom term to the bottom term, okay? And these are called Schwinger-Dyson equations, okay? And that's a double whammy. Anytime you hear Schwinger and Dyson in the in the name of an equation, it's very convoluted, and you want to punch yourself in the face when you work with it. Okay, but that's what it is. All right. What does it tell us? Okay, so let's try to get a feel for this. All right, and that's not always easy to do when it includes Schwinger and Dyson, but we'll try. Okay. So let's consider the simplest case where we only have one field, okay? And we know that when we take the variation of the action, it's basically going to give us something that looks like a Klein-Gordon operator operating on the field, right? That's the equations of motion, okay? So then for the n equals 1 case, I go back here to the monster, and I just set n equals 1, so I only have one term, right? So I have a time-ordered product, this thing times the field, and then one field in here, and these delta functions, okay? So, I guess I would have no fields in this round, I just have the delta function. All right, so I'm replacing delta S, delta phi with that stuff, right? And so it gives me a time-ordered product of those two operators. Or, if I simplify things, I can write it like this. And this is a what? Is a what equation? It's a Green's equation, right? And it's telling us that, what? It's telling us that for this theory, this guy is a Green's function, right? The propagator, the 2-point function is a propagator, is a Green's function for the theory, which is something that we already showed.
The bracket is the Green's function of that operator.
Right. Yeah. Right, and that's we showed it. God, I don't know how many, a long time ago when we were studying free Klein-Gordon theory. Okay, but this is just a different formulation of it. Right. So we can write the propagator like that, but we already did that. Okay. Well, let's consider a case where x, which is the argument of this derivative, is different from x1, x2, and all the other x's. Okay? So what that does is it means that these delta functions are 0, right? So this term goes away, and I just have to worry about the first term. Where am I? I completely got lost. Yeah, okay, so here I am, right? So I've got this term. Okay, so what do I want to do with it? Differs from those of all other fields, right? So it's telling us what? That the classical equation of motion is satisfied, right? Classical equation of motion is satisfied by a quantum field inside a correlation function as long as the space-time argument direction is okay. Okay, so it's telling me that basically that thing up there, when I put it in here, is basic. We know that the other fields can't be, the other fields in general aren't zero, right? So it's telling me that the equations of motion are satisfied. That makes sense, what I'm saying? So I have, where am I? Okay, so I have this term, right? Once I specify these cases where x can equal the other x's, okay? That means the second term of the Dyson-Schwinger equation goes away. And now I've got this equation, or this stuff inside, so this is a correlation function, right? It's got this this derivative here, and then some list of fields, right? And the fields are non-zero by definite or assumption or whatever. And I've got equals 0. Okay, but this thing you've already said is that, which is basically the equation of motion. All right, so I could plug that in here, and so it's telling me that that thing has to be 0 because I know that this stuff can't be 0. Okay, does that make sense now?
Basically, it can come out of the bracket.
Well, no, it's still in the bracket, but it's telling me that the time ordered product of these operators, because I know the fields can't be 0, it's telling me that that equation of motion there, that Klein-Gordon operator operating on the field, is what gives me 0. So let's go back and look at the statement that I wrote, which I can't believe I wrote it, but what this is telling us is that the classical equation of motion, the Klein-Gordon equation of motion, is satisfied by a quantum field inside a correlation function as long as the space-time argument differs from those of all the other fields. Okay? If this isn't the case, then we get those extra terms, right? We get that second part of the Dyson-Schwinger equation, right? We get those other terms. Okay? All right. So finally, let's consider a theory that has a continuous symmetry and the corresponding nether current. Okay, so I'm using the definition of the nether current that we had before. And we're going to dial this variation such that the variation of the Lagrangian vanishes. Okay, so that means that the divergence of the current is just going to be equal to this stuff. Okay. Then summing equation 22 is 22. Is that the Dyson-Schwinger? Okay, so we're going to take this, the result that we got from taking n functional derivatives, because we want to write down something that corresponds to the time-ordered product of operators. We're going to take summing equation 2 over the index A, and we're going to use this guy in place of, 22. So we're going to replace, it looks like this guy, the delta S, delta phi, with our current, okay? And if I do that, I do the algebra correctly, I get something that looks like this. So I have the 4 divergence, which I can pull outside of the correlation function. So I have a correlation function or a time-ordered product of operators with J mu, the current, right? Plus this other term, which is basically the contact terms is what they call them, right? And the sum of those two equals 0. All right, what does it tell us? I have no earthly idea. No, I'm just kidding. It's called the Ward-Takahashi identity. Okay, and it plays a very important role. Maybe it's not apparent from this equation, but it will become more. We'll talk more about it when we get into vector fields, because it plays a big role in computing, scattering amplitudes where you have external photons, okay, external vector fields, okay. But it basically tells us that the conservation of the nether current holds in quantum theory. How do we see that? Inside a correlation up there, yeah. So we see that in quantum field theory, right? So we have the current inside of a time-ordered product of operators, but this derivative is acting on this, is being contracted on here, and as long as there's no contact terms, as long as x is different from any of these xj's, that term's 0, and so the current, in this quantum field theory is going to be conserved. Okay. All right. Okay. So that's all I want to say about continuous symmetries. And like I said, we'll come back to it more and more as we start to construct other theories. Okay. So that's continuous symmetries. Now what I want to talk about are discrete symmetries. Right? We know from quantum mechanics that there's two very famous discrete symmetries. One is parity, and the other is time reversal. Right? But we have those same guys in quantum field theory. Okay. So continuous symmetries, such as the Lorentz transformations that we're always interested in, are called both proper and orthochronous. All right. I'm throwing out some big words today, some $10 words here. All right.
Sounds like a super villain.
Orthochronous. Yeah.
Something involving time.
Yeah. Yeah. Dr. Orthochronous. So proper just means that the determinant of the transformation matrix is +1. Orthochronous means that the 0, 0 component of a transformation matrix is greater than or equal to +1. Okay? Those are the definitions. All right? What we're interested in are transformations that aren't those things. Okay? Either one or the other, or maybe both. All right? So we know, so this is just summarizing stuff we know about continuous symmetries, especially in particular Lorentz transformations. We know Lorentz transformations, we can write them like this, right? Infinitesimal Lorentz transformations. We know that they're always continuously connected to the identity operator, plus some action, right? Some either propagation or rotation. Okay? And anytime we have a transformation like this, remember we can compound all the small transformations, and we end up getting something that looks like an exponential, right? But we can also write this down in matrix form, right? And in Minkowski space, it's going to look like this. So this matrix is continuously connected to the identity operator, and then our transformations look like this. Okay, and these guys, these M mu nu are the set of translations rotations that you're used to from Lorentz transformations. Okay. All right. So what we want to do is, in this case, so that's the case for continuous symmetries. We want to talk about the case of discrete symmetries. All right. So symmetries that aren't continuously connected to the identity operator. Okay. And like I said, the two most famous are space inversion or parity. Which looks like plus, minus, 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 so we're inverting the spatial coordinates, and time reversal, where you're inverting the time component of the transformation matrix. Okay. Note that by definition, the parity is orthochronous, but it's improper, so don't bring it to a nice fancy party. All right. And time reversal is non-orthochronous and improper. So time reversal is a real, you really don't want to take time reversal out on the town, okay? Oh yeah, so there's another one that we run into in quantum field theory, which is charge conjugation. And I don't remember if I cover that in this lecture, but we'll get around to it, okay? But these are real symmetries of nature, right? You always hear about charge, parity, time reversal, CPT, right? Or you hear about the CP violation, or whatever the other buzzwords are. These are the symmetries that they're talking about. Okay, so there are cases where we would think that these are symmetries of nature, and we use those to write down our Lagrangian, right? But there's been instances where they've noticed that there are violations, right? There are parity violations, and it's a good thing that there are. So I think it's CP violation. So the combination of charge and parity, because that's the reason that we're here, basically. So it leads to, in some theories, it leads to a dominance of matter over antimatter. Okay, so you can explain away why there's so much matter and so little antimatter. Right?
The CP violation.
Mm-hmm.
The CP violation
Mhm.
tells us so.
Yeah.
And it also means that we need stage annotation.
What tells us that we need 3 generations of quarks? I don't remember if that has to do
You
with.
can see the CKM.
Oh, that's a CKM matrix. Yeah.
Because of the CPY mentioned, one of them, I guess, this could be imaginary. I'm sorry.
No, you're right. You're on the right track. Yeah. We'll talk about that next semester. But yeah, you're right. It's all related. Yep. Okay. All right. So what are we going to do? Okay. So let's look at these transformations. Okay. So we know that we can always write down Lorentz transformations in this way. So we can take our field and hit it from the left and right with some transformation matrices, right? And it's the same thing as if we took the field and transformed its argument, space-time argument, right? So let me use some notation where I'm going to say P is what we would call this matrix for the parity operator, and T is what we would call this matrix for the time reversal operator. Okay, and so we would expect that by analogy from our case of continuous symmetries, that these types of relationships would hold up. Okay. The difference is, right, that the parity and time reversal transformations, if you look at their form, they're the inverse of each other, right? Okay, they're their own inverse. Okay, so that's going to introduce. I wouldn't call it a complication. It's just an interesting characteristic or feature of these symmetries. Okay, and to see that, let's consider taking one transformation and doing another transformation. So I'm flipping space and then I'm flipping it again. So I should get back to where I was, right? So let me take this equation and hit it from left and right by our parity matrix operator. That's what I'm doing there at the bottom, right? So we have something that looks like this, okay? So we have p to the minus 2, p squared, and that should be equal to p squared operating on x, but p squared operating on x, we already know is just x, okay? And so, what does it tell us? All right, so it tells us doing 2 of these transformations gets us back to where we were, right? And it makes physical sense because this is a Hermitian operator, right? So it's a Hermitian field. However, the fact that it obeys this type of relationship, but takes us 2 transformations to get back to where we were, it leaves open the possibility that the field doesn't just transform like we proposed here, right? It doesn't necessarily have to transform like this with a plus sign. It means that we could also have a transformation where the parity transformation takes it into a minus sign, right? Because that's my constraint up there with the parity operator. Okay, so if I operate again, I'll get minus 5 squared. Okay. Right, so just by convention, if the field transforms with a plus sign, we call it even under the transformation. And if it transforms with the minus sign, we call it odd. Okay. And if a scalar field is odd under parity, you sometimes hear it called a pseudoscalar. Okay. Because it's a scalar, but it changes under parity. You know what I mean? Right? Okay. All right, so this is when we write down our Lagrangian, we want to make sure we observe. Let's say we observe parity symmetry in nature, right? So that means that when we write down our Lagrangian, we don't want any terms that change sign, right? If we operate on it with a parity operator, so that'll dictate how we write down these fields, right? So I don't want any odd number of 5 fields, because if I do a parity transformation, I'm going to get a minus sign on that Lagrangian term, and I don't want that, right? So that's one simple example of how we use symmetries to build our Lagrangian. Okay. Oh, I guess I jumped ahead of myself. Right. So what we want is, like I said, when we do a parity transformation or a time reversal translation, we want the Lagrangian to not change sign. Right? We want it to be even under these transformations. Okay. Right. So the invariant. Okay. So yeah. So I'm just saying that the invariance of the Lagrangian under these transformation implies an invariance of the action, right? Just by definition. And that means that if you have some invariance under an action, that there are some symmetries that are conserved, right? Or currents that are conserved. And in this case, it's parity and time reversal. Okay. So if we require the Lagrangian to be to not change under parity, we say parity is conserved, or time reversal is conserved. All right, and so if you're wanting to take this, take these symmetries and construct a Lagrangian for our scalar field, say, obviously, if you just pick the even fields, you're going to be safe, right? But say, somebody went off and measured, and there's another field and has odd parity, so you have to include that in your theory, right? So what types of interactions can that field have? Well, it has to come in pairs, right? So if you have a particle, or so say you have a particle that somehow they measure the parity and they find it's odd, right? And so you scratch in your head and you say, "Damn it! I thought there was only even fields."
No, you say those damn experiments.
Yeah, what the hell are they doing? So you say, okay, well, let me make a prediction. Let me say, okay, well, I want parity to still be good, symmetry. I want it to still be conserved. So that means that if I call my, let's call that, I don't know, let's call this phi plus and phi minus, right? So these would be our two fields. These are the fields we wrote down because we've seen these fields for a long time. We've been producing them at whatever experiment. But then they did another experiment and they found these guys, right? So we say, okay, how can we include these guys? Well, they're going to have to come in pairs, right? Because if I want the Lagrangian to be invariant, I need this guy, which changes sign, to come in pairs, right? So I need terms that, are going to go like phi. So I could write down, and remember, we want our normalizable terms. We want, say, if we're working in 4 dimensions, so we'd have terms like phi squared, or phi minus squared, phi plus squared, things like this, right? So we would write down all the terms that obey our symmetries, right? This guy obviously obeys it. You could write down a term that goes like phi plus, and then phi minus squared, or phi minus to the 4th, phi minus whatever. You can write down any terms that obey the symmetry. Okay.
Phi cube, that means is the reason for it doesn't obey.
Well, it does if we just pick phi to be an even field. Yeah. Which, we haven't specified as parity or time reversal or quantum numbers yet. But if we pick them to be even, we're okay.
Each field, you mean the phi itself?
Yeah, phi is even under. Yeah. And any of you guys that are interested in supersymmetry should get out. No, I'm just kidding. If you're interested in supersymmetry, this is exactly what they call R parity. Right? So they try to explain. So let me tell you the story. I'm just going to end on this, and then we'll stop. So the story was they wrote down supersymmetric theories, right? And everybody was, yeah, and going crazy. These theorists are like rock stars. Then talked about grand unified theories and all this stuff. And then they went and looked at their theory and they said, "Oh shit, our theory predicts proton decay, and nobody's ever seen a proton decay before." So they said, "All right, what can we do here? We want to save face." They say, "Oh wait, there's some discrete symmetry. It's kind of like parity. We're going to call it R parity, okay? and we're going to make R parity a good symmetry. And what it did was it killed off the operator, the terms in the Lagrangian that led to proton decay, predictions of proton decay. So if you impose R decay, or R parity, you can get rid of proton decay, right, in your theory. Well, so then they were rock stars again, and now they're out panhandling for money and stuff because supersymmetry is nowhere to be found. But anyways, but what came out of that was another problem besides proton decay was a particle that's stable on the lifetime of the universe, very weakly interacting. In other words, dark matter. Right. So what happens is they used R parity to kill off proton decay, but R parity also meant that you had in your theory a stable particle, a supersymmetric particle that didn't decay down. Right. So typically, if you see somebody give a talk about supersymmetry, you'll see, the mass spectrum of all the, squarks and gluinos and all that stuff, right? And you'll see that if mass is this scale, they all decay down. It's almost like nuclear physics, right? They all decay down, but they hit a point where there's some particle that's completely stable. And it's completely stable because of this R parity, right? So R parity means you can't write down a term that, say, would couple it to, I don't know, fermions, right? So electrons, E minus E plus. So you can't write this term down, right? This would allow this thing to decay, right? Because it would decay into electron, an electron and positron. But the fact that you have R parity means this guy is odd under R parity, right? So that term goes away, and you end up with no terms that allow this hive, this particle, whatever it is, to not decay. Okay. So that's a real world example, simple example of like a parity type of symmetry that you impose on your theory. Okay. And it's become kind of the paradigm for beyond the standard model theories of dark matter. So every theory that that you can write down about dark matter, you have to explain why it doesn't decay, right? Why it doesn't decay down into standard model stuff, and it's always some discrete symmetry, whether it be a Z2 symmetry or some other discrete symmetry. But it's used all the time. Okay. All right. So I'll stop there and. We'll pick it up next time. We'll talk about some discrete symmetries, okay? All right.